On January 3rd, 1961, the first fatal nuclear reactor accident in the United States, an uncontrolled nuclear excursion, occurred at the Atomic Energy Commission's SL-1 facility at the National Reactor Testing Station, better known as NRTS, in Idaho. All three men performing maintenance on the reactor during shutdown were killed. Immediately after the accident, a three-phase recovery program was initiated. Phase 1, lasting 6 days, consisted of executing pre-planned emergency procedures, recovering the casualties, and determining the extent of radioactivity release to the environs. During Phase 2, from January 10th, 1961 to late April 1961, Combustion Engineering Incorporated, the SL-1 operating contractor, was responsible for determining the nuclear safety status of the reactor. Safety being a paramount consideration, no personnel were allowed to enter the reactor building during this period. All investigating, viewing, and probing was accomplished with the use of remotely operated equipment. With the aid of TV systems, photographic equipment, and water and temperature detecting probes, the core was determined to be devoid of any moderating water, and the reactor was declared nuclearly safe. The Commission has issued a separate motion picture on phases 1 and 2 of the SL-1 accident. Phase 3 of the accident recovery effort was aimed at discovering what caused the nuclear excursion. A contract for this portion of the operations was awarded to the General Electric Company. Its responsibilities were to gather evidence pertaining to the accident, prepare the facility for core removal, recover the core for examination, demolish the reactor building, decontaminate the SL-1 site to habitable status, and as a fact-finding group, present an accident analysis to the AEC. To understand Phase 3 work better, it is essential to review the situation as it existed before and after the accident. The accident occurred in the reactor building, which is divided into 3 main areas. The uppermost section contained an air-cooled condenser with associated louvers, fan, and motor. The middle portion was the main operating area, where the reactor head was located, slightly below floor level. The control rod drive mechanisms penetrated the reactor head. Biological shield blocks surrounded the head during operation. The lower portion of the building housed the reactor vessel with a core in the lower region. Around the core was a gravel biological shield. During the interval between January 3rd and May 17, 1961, the state of the reactor operations room had not been disturbed. Essentially, all items and debris were in their original post-accident location. The shield blocks were in the same place as in pre-accident maintenance, having been moved back for access to the reactor. Vessel insulation material, steel punchings, fine gravel, and blotting paper were strewn over the floor. One of the control rod shield plugs, ejected from the vessel head nozzles, was lodged in the damaged ceiling. 2 other shield plugs could not be accounted for, but were later found in the overhead fan room. A 4th plug was observed to be lying across the reactor head. Any attempt during Phase 2 to move or disturb this component might have jeopardized nuclear safety. For example, by causing precariously perched fuel to fall into the core region. Remote viewing access to the vessel interior was limited to the only nozzle that was completely unobstructed. However, evidence that the core was dry permitted removal of the interfering plug by remote means. TV monitoring greatly facilitated this task. Greater photographic exploration of core damage was now possible. The plug was taken to one of the laboratories used for analysis work. This work proceeded simultaneously with a site recovery effort. Now, before commencing extensive decontamination efforts on the building, definite steps were taken to prevent physical hazard to working personnel. As standard procedure, participating personnel were thoroughly briefed beforehand at a control point 500 feet from the SL-1 site. Each man was made aware of his assignment, time allowed, health physics procedures, and what to do in case of unforeseen accidents. Nuclear detectors installed soon after the accident were routinely checked to ensure their operability as an early warning in the event of further nuclear activity. The reactor was deemed nuclearly safe as long as nothing was done to change its unmoderated status. Threatening this status was a 1,000-gallon tank of demineralized water suspended from the ceiling of the reactor operations room. On June 2nd, 1961, the first personnel entry into the reactor building since January 9 was to drain the tank in the operations room. The crew attached a garden hose to the tank and drained the water to the ground after making sure it was free of contamination. Another early safety precaution was the removal of oxygen and acetylene bottles and other readily combustible materials from the operations room floor. In event of fire, water could not be used for fear of causing another criticality should it get into the core. Evaluation of various plans for core removal and site cleanup depended on knowing the pattern of radioactive contamination within the building. Synchronized photo and radiation surveys of the operations floor indicated a nearly symmetrical zone of radiation. In the 5 months since January 3rd, the levels had dropped from more than 1,000 R per hour to approximately 150 R per hour over the reactor, decreasing radially to approximately 30 R per hour at the building perimeter. To determine how much of the radiation was coming from the reactor proper, the bags of lead shot were inserted into the open reactor nozzles. This lowered the overall radiation less than 10%, confirming that the accident had spread high-level contamination throughout the building. Also, that a major decontamination program faced the contractor. Scattered insulation and blotting paper had tended to concentrate the contaminated water from the reactor vessel into high sources of radiation. Recommendations based on the contamination study were made to an ad hoc committee which had been appointed by the AEC to evaluate and propose final disposition of the SL-1 reactor. A plan was agreed upon for removing the reactor vessel, complete with core, to a large hot shop at the north end of the site for dismantling rather than dismantling them in place. By June 1961, lower radiation levels and the assured nuclear safety made it feasible to proceed with direct rather than remote decontamination and dismantling of the building. December 1 was set as the target date for removal of the reactor vessel in order to avoid adverse winter conditions. Donning anti-contamination clothing, large numbers of recruits assisted in the cleanup activity. Each man wore a belt containing 18 film badges to monitor the highly directional beta radiation exposure. Complete taping and masking controlled body contamination and inhalation of radioactive aerosols. Fine particulate material tended to penetrate even 2 sets of coveralls, so a disposable plastic suit was worn for additional protection. Self-reading dosimeters were taped to the suits to provide on-the-spot monitoring of exposures from radiation. Vacuum cleaning was a major decontamination technique. An improvised vacuum system developed through operating experience consisted of 50 feet of hose running down from the working area to a 15-horsepower positive displacement rotary blower with a shielded 55-gallon collection drum and bags mounted on a truck bed. Gross clutter such as iron punchings, blotting paper, and insulation had to be shoveled into cans. These cans now represented new concentrated sources of radiation and were removed by remote means through the freight door. Another remote removal method was the use of an electromagnet to remove iron punchings from the higher fields of radiation. It met with limited success. All loose debris retrieved from the floor was shipped to the hot shop for inventory. Every item that might improve understanding of the accident had to be examined. As the cleanup progressed, the contaminated concrete blocks proved to be major obstacles as well as being sources of radiation. The heavy blocks were skidded across a greased steel apron to the freight doors and allowed to drop onto a pile of sand, which served as a shock pad to prevent breakup. To minimize exposures, cleanup near the reactor was left until last. This area, including the reactor head, was now the highest source of radiation. Temporary shielding in the form of a 2-inch steel plate was placed over one particularly high source of radiation next to the reactor. Also, bags of lead or steel shot were placed over and around the head. Radiation on the operations room floor, except over the reactor head, was now down to 15 R per hour generally. But a radiation survey of the ceiling indicated major levels of radiation. The excursion had forced contaminated water and debris through holes in the damaged ceiling. Originally, a ladder and narrow airlock provided access to the fan floor. Safer and easier access was gained by cutting through the outside wall of the building and erecting a large outside stairway to the fan room level. Preceded by a health physics survey, a photographer entered the reactor building to obtain photos of the general conditions. These photographs were used to brief personnel, spotlighting key items to be collected as cleaning progressed, such as shield plugs, pieces of drive racks, and broken C-clamps. Floor vacuuming was again employed, followed by placement of 1/4-inch iron plate on the floor for personnel shielding. Cleaning efforts continued alternately in the fan room and immediately around the reactor head as radiation levels dictated. During the first 2 months of Phase 3, entry times were in the order of 1 to 3 minutes, resulting in a total of only 16 man-hours of cleanup in the reactor building proper. A bell alarm system installed in the working areas was used to control how long workers could stay in the reactor building. Despite general cleanup of the fan loft, radiation sources in excess of 50 roentgens per hour remained within the relatively inaccessible parts of the condenser gear. In order to lift the pressure vessel, the fan, condensers, and ducting had to be removed. The contaminated fan room components were cut from their mountings and lifted from the building. Safety ropes were required for all high elevation work. To protect the reactor vessel from inadvertent flooding by rainwater, a protective plate was placed over the roof hole during non-working hours and bad weather conditions. The removed equipment lying around in the SL-1 yard soon posed an additional problem in the form of unnecessary background exposure to personnel. A careful study confirmed the desirability of opening a new burial ground specifically for SL-1 debris. The survey indicated that 81,000 cubic feet of burial space would be needed. The estimated personnel exposure that would have been required to cut, package, and transfer the contaminated equipment to the existing NRTS burial ground would have exceeded the contractor's allowable exposure for a 3-month period. This consideration alone justified opening a new burial site 1,600 feet away from the SL-1. Also avoided was possible contamination of 13 miles of site and public roads leading to the more distant NRTS burial ground. All material not being directly examined for accident evidence was transported without any decontamination to the burial trenches north of the SL-1 site. trenches were backfilled to approximately 2 feet of overburden, or until radiation readings were less than 1 MR per hour at the ground surface. Removal of the grossly contaminated equipment enabled personnel working in more tolerable radiation fields of less than 5 R per hour to prepare the vessel and building for extraction of the reactor. The core structure had to be carefully inspected to verify whether it could withstand the 40-mile transport to the hot shop. A borescope examination of the underside of the core through an 18-foot long hole bored through the gravel basin vessel wall indicated that the core structure would remain intact during the move. Some 60 photographs were made through a 26-foot borescope which contained its own light source. Large segments of insulation from around the vessel walls were found on the reactor room floor, indicating that the vessel may have raised several feet at the time of the excursion. A trial lift of the vessel was performed with a building service crane. This operation confirmed that the 13-ton vessel had jumped, shearing off the steam outlet and feed water pipes. This freed it to be raised from its supporting shell. Observers actually saw the sheared steam outlet as the vessel reached the peak of its 3.5-foot trial lift. The entire operation was monitored and directed with the aid of closed-circuit TV. The vessel was now ready for removal as soon as a 7-foot hole could be cut in the operations room ceiling to accommodate the actual lift. Partial cutting away of the fan room walls also was necessary in order to allow clearance for the bottom of the vessel and optimum positioning of the 60-ton capacity crane. To minimize the possibility of mishap, a complete mock-up operation was conducted just prior to the actual transfer. A concrete cylinder of approximate dimensions and weighted with gravel was used to test clearance, positioning, and maneuverability for the final lift. The simulated vessel was test hauled to the site in an available concrete cask, which was to provide radiation protection during the transport of the vessel and core. Additional gravel was spread next to the building to afford a level pad and a contamination-free surface for the truck tires. The mock-up exercise showed that 6 inches of additional building shell had to be removed to attain the necessary clearance. To contain and minimize the spread of contamination from the vessel proper, rubberized canvas with elastic bands was positioned over the top of the reactor on a steel frame. As the vessel was withdrawn, the accordion-like shroud automatically enveloped the vessel. As a final precaution against contamination, the tractor and lowboy trailer were covered with sheets of plastic. The actual lifting and removal then proceeded smoothly. The entire operation, including transfer of the vessel to the trailer, required about 20 minutes. Radiation levels around the unshielded vessel during the transfer measured about 9 R per hour at 25 feet. Prevailing good weather contributed to ideal operating conditions. The metal top was used to confine any loose contamination during transport. The following morning, November 30, 1961, the truck and cask were stripped of their protective plastic covers and steam cleaned. Direct radiation readings were only 40 to 50 milliroentgens per hour at the surface of the cask. The 40-mile trip to the hot shop was accomplished without difficulty in less than 4 hours. The route had been cleared of overhead obstructions to accommodate the 24-foot high load. Precautionary surveys made sure that all bridge capacities were adequate for the 52-ton weight. The caravan, complete with emergency crews and tire-changing equipment, did not disrupt the normal flow of traffic. 6-story, 160-foot-long hot shop, equipped with remote manipulators, was ideally suited for the extensive task of vessel and core examination. It was originally used in the aircraft nuclear propulsion program. After removal of the vessel, there remained the work of raising the silo-like reactor building and decontaminating the adjoining buildings and grounds. The fan room walls were cut with torches and removed with a crane. The heavy fan room floor was cut into 3 segments. The largest section with supporting I-beams was removed last. Despite the unique problems encountered, only one minor accident occurred during the recovery work. Further reduction of radiation exposure was accomplished by cleanup of loose contaminated debris after the vessel removal. Then followed removal of the operations room motor control panel, purification panel, turbine generator, pumps, piping, and walls, and eventually the stairway. Practically all that remained at that point was the concrete reactor operations floor and the lower shell of the building filled with gravel, which was spilled through weep holes and removed for burial. The 700 cubic yards of gravel was not highly contaminated as originally estimated. It ranged from 3 MR per hour for a handful of gravel taken from near the outside wall to 10 MR per hour for a sample that adjoined the reactor vessel support cylinder. Particulate airborne contamination was held to a minimum and careful surveillance was maintained by health physics personnel. It was decided that blasting would simplify removal of the 70-ton concrete floor. Preparation for this included cutting the wall, removing the superstructure, and placement of fallout paper at strategic locations to monitor aerosol contamination resulting from the blast. 2 experts were called upon from the Army Demolition Section at Fort Belvoir, Virginia, to cut the 6 remaining I-beams supporting the concrete slab. 2 days were expended in planning the demolition job, including preparation of the composition C explosive in shaped charged trays. The explosive was strategically placed to make sure the slab of concrete and steel would not fall against the surrounding buildings. Trucks then removed the remaining gravel and the steel support cylinder. Sectioning and disposal of the base plate upon which the entire building was erected came next. The remaining steel reinforced concrete piers, which supported the entire structure, yielded only with the help of a bulldozer and cutting torch. The radiation level at the surface of the ground where the reactor stood was finally reduced to less than 1 MR per hour by blading and backfilling with clean gravel and dirt. In all, it took 5 months to complete demolition of the reactor building. Meantime, decontamination of the adjoining buildings went forward using proven techniques. Vacuuming was ideal for decontaminating porous acoustical ceiling tile. The loose insulation in the attic of the support building was contaminated above allowable limits. It had to be removed by hand or by vacuuming. Salvageable items, such as telephones, desks, chairs, vending machines, tools, machinery, and control room equipment, went to the control point for decontamination. The more unwieldy or complex items were transported to the decontamination area. Gross steam cleaning and acid baths were employed on heavier equipment. The more delicate instruments were hand cleaned. High-pressure hosing of the exterior metal walls